Welcome to Ask and Learn.
In this exercise, we have a hollow cylindrical spool that has a mass m, an inner radius r over 2, and an outer radius r. And it's free to rotate around its center. And there is a mass attached to a wire that's wrapped around the spool that has a mass m. This is the counterweight. And when the spool starts rotating, due to the counterweight weight, the counterweight falls initially from a time t equals 0 to a time t, a distance of y. And with these informations, we want to calculate what is the torque that the friction forces exert on the spool due to a horizontal axle that passes through the center of the spool. So tau f is what we want to calculate. So what I'm going to do is to write the force equation for both the counterweight and the spool itself. So for the counterweight, we have the weight force pulling it down. So I'm going to call it W. And then we have the tension force pushing it up. So we have the weight force, that's mg, minus the tension, and that's equal to m times the acceleration a of the counterweight. Now notice that delta x is equal to v0 t plus at squared over 2 for uniform acceleration. In our case, delta x is just y, that's how much the counterweight fell. V0 is just 0, and this is equal to at squared over 2. So a is equal to 2y over t squared. This means that mg minus t is equal to 2my divided by t squared. And from here we can obtain the tension force, and that's equal to mg minus 2y over t squared. This is the tension. We're going to keep it because it's going to be useful. And then we have to calculate the total torque on the spool. Now notice that there is the tension force acting perpendicularly to the spool, and it acts at a distance of r, and then we have the friction force that acts upward at a distance r over 2. So we have the friction force, and I'm just going to call it Ff. So the total torque, tau, will be the torque exerted by the tension, that's Tr, minus the torque exerted by the frictional force, that's Tf, and this is equal to the moment of inertia I times alpha. Now, the moment of inertia I for a hollow cylinder is equal to m over 2 times the radius of the outer radius of the cylinder plus the inner radius of the cylinder, both of them squared and summed. And alpha is equal to the acceleration divided by the outer radius. Now, the acceleration in our case is equal to 2y over t squared, and the outer radius is just r. And if we want to calculate I, this is equal to m over 2 times the outer radius squared, which is r, plus the inner radius, which is r over 2 squared. So this is 5 m r squared over 8. So what we obtain is that Tr from this equation here for the torque equation, Tr minus tau F is equal to 5m r squared over 8 times 2y over t squared r, and this is equal to 5m r y over 8 over 4 t squared. So this means that tau f is equal to tr minus 5mry over 4 t squared. So if we just isolate r here, we have r times t minus 5m y over 4 t squared, and t is equal to m times g minus 2y over t squared minus 5my over 4t squared. And this is exactly what we wanted to show, that the tension, actually the torque due to the frictional forces, is.